Now part B, we're given another set to look at, the image of T. What's the image of T? It's the set of all T of V's, so that V, the vector V is in V. So this is a subset of W. And in other textbooks, this is called the range of the function. If you think of range from college algebra being the set of outputs, then really what we're talking about is the range of this function T. All right, we want to prove this is a subspace of W. And so what's the subspace criteria? Is the zero vector in W part of this thing? And two, if two vectors are in there, and I'm going to call them W1 and W2 so we don't get confused. If W1 and W2 are in there, is their linear combination in there. Okay, so it's the same subspace criteria we've had since the beginning of chapter 2. All right, so number 1. Is the zero vector in there? Well, how does the zero vector get in there? The zero vector has to be T of something. So am I guaranteed that there's something in V that's going to be shipped to the zero vector? And the answer is yes, the zero vector in V. So since V is a vector space, V has an additive identity. Since T is linear, we know that T of the zero vector in V is a zero vector in W. And that's what it means to be in there. Hence, the zero vector of W is in the image of T. Why? Because there's something in V that got that was sent to it by the function T. 2. Let W1 and W2 be two fixed but generic vectors in the image of T, and let alpha and beta be two fixed but generic real numbers. Okay, so what does it mean? For this to be in there, there has to be some vector in V that gets sent to this. All right, so let's start looking at working with the definition. W1 and W2 are both in the image of T. What's that mean? That means that each of them comes from some vector in V. There is a vector V1 in V with W1 equal T of V1. And there is a vector V2 in V with W2 equal T of V2. The challenge is, right, I need to find some vector V in V so that T of V is alpha W1 plus alpha W2. Well, T of V is a linear combination of W1 and W2, but W1 and W2 themselves are the images of V1 and V2. So, using linearity, I know that linear combinations are preserved under linear transformations. So I have a linear transformation of the images of V1 and V2. By linearity, that's the image of the linear combination of V1 and V2 themselves. So this is the guy that's going to be shipped to this guy. All right, so what do we do here? We need to show that this is an element of V. Okay, well, it's an element of V because V is a vector space. Since V is a vector space, alpha V1 plus beta V2 is in V. Since T is linear, T of alpha V1 plus beta V2 is alpha T of V1 plus beta T of V2. And by definition, T of V1 is W1 and T of V2 is W2. So here's something in V that gets shipped to alpha W1 plus beta W2. That's what it means to be in the image of T. So since the image of T satisfies the subspace criteria, the image of T is a subspace of W. So the kernel is a subspace of V, the domain. The image is a subspace of the codomain W. And we'll see how the image and kernel play off each other in the weeks to come. That'll do it for Quiz 12.